morning, distinguished guests, ladies and gentlemen. Welcome to the Materials for a Sustainable Future panel at the Science for Life Symposium. And this is the first event in the framework of VinFuture Scientific Week, VinFuture Prize Award Ceremony 2024. One more time, thank you so much for being here with us today. Thank you. Distinguished guests, ladies and gentlemen, the VinFuture Prize is a prestigious global science and technology award proudly originating from Vietnam. And the topics we'll explore in today's panel are essential for advancing global scientific progress and have profound implications for human life. Vietnam is deeply committed to supporting scientific development and is playing an increasingly influential role on the world stage. With a national goal of reaching net zero emissions by 2050, Vietnam is especially focused on expanding its renewable energy sector and advancing material science to disseminate scientific and technological knowledge to the public and connect generations of young scientists, inventors, and entrepreneurs with globally established inventors for potential partnerships. This event is held with the participation of distinguished speakers who have excellent expertise and experience in the field of materials and energy. And coming to this event today, in addition to our speakers, we are honored to have many representatives working in the field of science, technology, and also from government. We are honored to have Associate Professor Vũ Hải Quân, member of Party Central Committee, President of Vietnam National University, Ho Chi Minh City. Welcome, sir. It's our honor to have Professor Sir Richard Henry Friend from University of Cambridge, United Kingdom, also the chair of VinFuture Prize Council and the chair of this session today. Welcome, sir. And we are honored to have Ms. Lê Thị Thu Thủy, Vice Chairwoman of Vin Group. Last but not least, we also have Dr. Lê Thái Hà, Managing Director of VinFuture Foundation. Thank you very much. And to begin today's panel, and as well as the series of Science for Life Symposium, we would like to invite the President of Vietnam National University, Ho Chi Minh City, Associate Professor Vũ Hải Quân, to the stage for the opening speech. Please welcome.
Professor Sir Richard Henry Friend, distinguished professors, speakers, esteemed guests. Today marks an important milestone as we gather to address some of the most pressing challenges facing humanity, the pursuit of sustainability through scientific and technological innovation. As we stand at the crossroads of opportunity and responsibility, the role of material science becomes increasingly pivotal. Materials not only serve as foundation for technological advancement, but also as an enabler of sustainable solutions to the environmental and energy crisis we face. This symposium, therefore, is just not a forum for academic exchange. It is a space where ideas and solutions take root with the potential to shape a better future for generations to come. We are privileged to have an extraordinary assembly of experts who have devoted their career to pioneering research and groundbreaking innovations. Allow me to introduce our distinguished speaker, Professor Martin Andrew Green from the University of New South Wales, Sydney, Professor Thục Quyên Nguyễn from the University of California, Santa Barbara, Professor Marina Freitag from Newcastle University, Professor Seth Mather from the University of Colorado Boulder, moderating this section is Professor Sir Richard Harry Friend from the University of Cambridge. As the chair of the VinFuture Prize Council, Sir Richard presents a legacy of scientific excellence and commitment to advance solutions for the global challenge. We are truly grateful for his leadership today in dialogue. Today's discussion will center on several critical topics, including energy use and environmental implications of batteries, the environmental impact of energy materials, sustainable solutions for solar cells, advancing the efficiency for solar cells. These topics are not just technical challenges, they are deeply connected to society, well-being, environmental preservation, and economic sustainability. I am confident that today's discussion will spark new insight and inspire collaborative efforts to tackle these issues. At the heart of this conversation lies a shared vision, a world where science and innovation contribute to the suitable development and equitable progress. As we listen to the ideas presented by our esteemed speaker, I encourage all of us to think beyond individual disciplinary and explore the synergy that can drive holistic solutions. I would also like to take a moment to acknowledge the incredible work of VinFuture Foundation. By fostering global collaboration and celebrating scientific achievements that benefit humanity, the Foundation plays a vital role in advancing our shared goals. Events like today's Symposium are a testament to their commitment to shape a better future. In closing, I will emphasize the importance of collaboration. No single individual or nation can tackle the complexity of sustainability alone. It is through partnership, knowledge sharing, and a unified vision that we can drive meaningful change. I am confident that under the guidance of Professor Sir Richard Harry Friend, and with his insight from our distinguished speaker today, Symposium will be a platform for transformative ideas and impactful solutions. Together, let us take a step closer to realize a future where scientific advancement serves as catalyst for sustainable and prosperous world. Once again, thank you for your presence and participation. I look forward to stimulating discussion ahead and to additional outcomes that will emerge from this event. Thank you so much.
Thank you very much, Associate Professor Vũ Hải Quân, for your speech. Ladies and gentlemen, and now may I have your attention on the main screen to have a watch with the introduction video, and we will know who will be the chair and also who will be the distinguished speakers in our symposium today. Video, please.
Climate change and resource depletion are creating negative impacts on humanity, affecting every aspect of life. According to the Potsdam Institute for Climate Impact Research, climate change could reduce global income by 19% by 2050. Damages in sectors like agriculture, labor productivity, and infrastructure may cost up to $38 trillion annually. Fossil fuels like coal, oil, and natural gas account for a major share of global CO2 emissions. UNEP reports that the energy sector is the largest contributor, responsible for about 73% of total greenhouse gas emissions. In this context, the development of green materials is becoming a core factor in protecting the planet from the negative impacts of climate change and resource depletion. Green materials offer superior capabilities for harvesting and storing renewable energy, significantly reducing carbon emissions in industrial processes. In addition to optimizing energy efficiency, they promote the transition to a green and circular economy becoming the foundation for a sustainable and harmonious future. To gain deeper insights into this urgent topic, the VinFuture Foundation is honored to introduce the symposium materials for a sustainable future as part of the 2024 VinFuture Sci-Tech Week. The symposium will be chaired by Professor Sir Richard Henry Friend, University of Cambridge, United Kingdom Laureate of 2010 Millennium Technology Prize, and Chair of the VinFuture Prize Council. The symposium also featured speakers who are renowned figures in the field of materials and sustainable development, including Professor Marina Freitag, Professor of Energy in Royal Society University, Research Fellow at Newcastle University, United Kingdom. Professor Martin Andrew Green from University of New South Wales, Australia, Laureate of 2022 Millennium Technology Prize and 2023 VinFuture Grand Prize, member of the VinFuture Prize Council. Professor Seth Marder, Director of the Renewable and Sustainable Energy Institute, University of Colorado Boulder, USA. And Professor Thục Quyên Nguyen, Director of the Center for Polymers and Organic Solid, University of California, Santa Barbara, USA, Chair of the VinFuture Prize Pre-Screening Committee. Aligned with the theme of resilient rebound for the VinFuture 2024 awards ceremony, let us explore a new era of green materials, the solution for a sustainable future.
Thank you very much, our distinguished guests, ladies and gentlemen, for your attention on our introductory video about our topics today. And now, please join me in welcoming to the stage Professor Sir Richard Henry Friend, Director of Research in the Department of Physics at the University of Cambridge, Chair of the VinFuture Prize Council, and the Chair of today's symposium to deliver the opening speech for our topic, Materials for a Sustainable Future.
Okay, right. Well, good morning and welcome. It's a great privilege for us all to be here. It's always a great pleasure to come to visit Hanoi and to get a sense of the energy and of the future that we're so conscious of when we are here. Today's symposium is about materials for energy. Energy is something we consume a lot of. That's the problem with carbon dioxide generation. It's not just that there's a little bit of it. Each of us, on average, generate tons of the stuff every year. But we have options, which we're going to hear about today. We're going to have a particular focus on solar cells, where in the space of not much more than a decade, what seemed to be possible but not really affordable has become completely affordable. The cost reductions, the performance improvements have given us the toolkit we need to have a net zero energy economy if we choose. But to come back to that issue of scale, we need to deploy huge amounts of renewable energy, and that involves a lot of material. And in different ways, we have an excellent panel of keynote speakers we're going to hear from shortly. We're going to explore, in part, what is technologically possible, how there is much more to do to bring a zero-carbon future within our grasp, but also to understand what the downsides are, what that huge scale of materials usage must require us to do to be able to achieve a sustainable future with, from cradle to grave, management of many, many natural resources. So that's the small task ahead of us in the next hour or so, and I look forward to the inputs from our keynote speakers. Thank you.
Thank you very much, Professor Sir Richard Henry Friend, for your speech. Distinguished guests, ladies and gentlemen, and now we would like to introduce to the stage Professor Martin Green, Scientia Professor at the University of New South Wales and founding director of the Australian Centre for Advanced Photovoltaics, And Professor Green has received numerous prestigious international awards, including 2022 Millennium Technology Prize and 2023 Queen Elizabeth Prize for Engineering and 2023 VinFuture Grand Prize. And now please welcome Professor for the first presentation on the silicon's future trajectory in the advancement for solar energy technologies. Professor, please, it's your time.
Well, thank you very much. It's also a pleasure for me to be here again in Hanoi, so very much enjoyed my stay here last year, and it's great to be back. So, in keeping with the topic of today's discussion, I'll be talking about the role of silicon technology in our sustainable future. So silicon is the technology used in the present commercial solar cells, as Richard mentioned, that have seen dramatic cost reductions over the last decade. So this is just a snapshot of what's happened over the last decade, whereas Richard mentioned the costs have come down very dramatically. So on the left there is shown a solar panel from, 9 years ago. So you can see the size of it. It was 16% efficient. So that means 16% of the energy in the sunlight falling onto that panel gets converted to electrical energy at its terminals. But since then, you can see there's been a few physical changes in the panels. So they've grown enormously. So the panels there on the right show the size of a modern panel. So they've grown to about 2.4 meters tall, which is about 8 foot. And that measurement's not a coincidence. That's the biggest size that you can fit upright in a 40-foot shipping container. So the size of the panels is dictated by the way they're transported around the world. And transportation costs are an important factor in the overall costs of solar technology. And the more efficient you can make the panel, the lower those costs become as long as the associated costs, like the costs of interconnecting the panels in the field or wiring them up, the amount of copper you need, all those kinds of things are very much impacted by the efficiency of the panel. So that's been something that's changed over the last 10 years as well. So the best commercially available panel is now 24.6% efficient, so a big improvement over the 16% that was the standard not so long ago. The other thing you'll notice, the solar cells in the older panels are square, but now they're rectangular. So you can judge the age of a solar panel by just looking at the cells. So if they're rectangular, it means they're panels from the last 5 years. The technology has changed enormously over that period, as we'll see. Making the panels making the cells rectangular means you can use a larger silicon wafer in the production process that reduces the production costs, and then the cells are cut into smaller sizes within the panels. Okay, so one of those big panels generates under bright sunshine 1 horsepower. So now when I see a solar panel, since I've realised this, I can see a horse. So every solar panel is capable of generating as much energy as 1 horse. So you see a big field of panels, you can imagine all those thousands of horses slugging away doing something useful. The energy conversion efficiency is quite important, and that's where my team at the University of New South Wales in Sydney has made its major impact. So the chart on the left there just sort of shows the history of the efficiency of laboratory silicon cells. So it's getting on to 84 years ago the first silicon cells was made, and in the US in Bell Labs. And then during the 1950s, there was, with the development of semiconductor technology and the birth of transistors and so on, the industry really took off. And solar cells found use on spacecraft. So that pushed the efficiency along, as you can see there. We started work 50 years ago, 1974, celebrated the anniversary last week. And we were able to take the efficiency, improve it by an extra 50% relative, up to 25% efficiency by 2010. So that's just the team of enthusiastic young researchers that were involved in that activity shown there. Since then, there's been a range of cell technologies, and the main emphasis has been on improving the efficiency, because, as I mentioned, that's very important in determining the overall cost of the solar energy. And there's 4 technologies now that are used in commercial solar cells. So the first 2 were ones that were developed in our effort at the university, PERC and TOPCon, who are the main 2 competing technologies. So each of these, as you move down from top to bottom, has a higher efficiency in the laboratory. So the little dotted line along the top of the chart on the left shows the limiting efficiency for a silicon cell, which is just less than 30% efficiency. And the best laboratory cell now is 27.4. So getting quite close to that efficiency limit. The top 2 technologies are the 2 ones used mainly in production at the moment, but the industry is steadily working down this list to the more advanced technologies, higher efficiency ones at the bottom. So this chart just sort of shows the percentage of production from the different technologies. So the blue technology on the left there is technology developed during the space program in the USA, and it dominated for over 40 years, the production. But over the last 10 years, there's been this massive change within the silicon manufacturing industry. So there was a transition from that technology to a more advanced PERC cell technology that was developed in our labs. And at the moment, we're making a transition from that to TOPCon. So the industry is moving very quickly in terms of the silicon technology involved. And this is just projecting a bit further down the future. It's expected that we'll move right down this chart to the highest possible efficiency technology. You know, the challenge is that each of these technologies becomes more difficult industrial to manufacture. But as the industry becomes more experienced, it's able to tackle the industrial challenge at implementing these advanced technologies cheaply. And that's what's happening now. So we're progressing to the highest efficiency technology. The really important thing, of course, about solar is how the cost is reduced, and the chart on the left there just sort of shows the annual average selling price of solar modules over the last 10 years or more, and you can see the precipitous drop around 2009, dropping below $1 per watt of output, and then the grey regions just show regions of undersupply of some of the materials that you require in cell manufacture. So the industry growing so quickly that it can drain the supply of materials required in the manufacture. So that slows down the progress, and then off it goes again. So now you can buy one of those panels I showed earlier for less than 10 cents a watt. And those panels are 700 watt rating, so that means $70 for that big panel that can generate as much energy as a horse. The chart on the right just sort of shows how the number of panels supplied each year has grown. So that's measured in gigawatts. So that's like the output of a large coal or nuclear power plant. So you can see last year, 2023, there was 444 gigawatts. So that's starting to be a substantial input into our total world energy production, the equivalent of 440 coal-fired power stations worth of solar. But the good thing about that graph is it's expected to keep growing very quickly, and we're going to get up to 1 terawatt over the next couple of years. So that's 1,000 gigawatts of solar production. So lower costs, increasing installation. So what comes longer term? And this leads me on to tandem stacks of cells. So silicon runs out of performance potential at about 30% efficiency, but if you stack cells from other materials on top of silicon, you can improve the efficiency further. So the chart on the right just sort of shows a number of cells that you include in the stack. With one cell, you can get about 30% efficiency. If you stack 2 cells, you can get over 40% in principle. 3 cells, you can get close to 50%. So it's a mechanism for improving the performance. Each cell in the stack is specialized for a different color within the sunlight spectrum, and that improves the overall efficiency of the conversion process. So the challenge is to find materials that have the same desirable properties as silicon. Like silicon's an ideal material for solar in that it's abundant, it's non-toxic, it produces very stable solar cells, and it produces efficient solar cells. So those are the four criteria you need, I think, for one of these materials that you stack onto silicon that we're going to hear more about in the symposium. And I've just got a list there of all the candidates and how they fare on those four criteria. So we're going to hear about perovskites and organic solar cells, which are two of the key contenders for including in such stacks. And as you can see, there's some ticks and crosses. You know, with perovskites, there's a lot of lead involved. It's mainly lead, although the cells are very thin, so it's not a huge amount of lead. And stability is the main issue, as with a lot of the other technologies listed there. So you've got perovskites, organics, and then you've got these compounds of materials that if you stitch together in the right proportions, you can produce what I think of as synthetic silicon. So you can engineer their properties so that they're good at converting blue light, for example, that silicon's not great at converting. So that's the future, I think. Initially stacking the cells onto silicon to take advantage of the huge industries that's supplying these hundreds of gigawatts of panels internationally. And then as you stack each cell onto silicon, you reduce the contribution of silicon to the final output. So I think the final embodiment of solar technology will be a stack of thin film cells without the silicon needed. So I think, while silicon has been the vehicle for progress so far and is fully capable of delivering, the lowest electricity costs in history, I think, ultimately, if we're successful in our research, we'll displace the silicon entirely and just use these thin films deposited perhaps onto glass as our final technology. So thank you very much for your attention.
Yes. Would you kindly give a round of applause for the Professor Martin Green? Thank you very much for your presentation on silicon's future trajectory in the advancement of solar energy technologies. Distinguished guests, ladies and gentlemen, and now I would love to welcome to the stage Professor Marina Freitag, Professor of Energy and Royal Society University Research Fellow at Newcastle University, to deliver the second presentation on advancing solar energy, integrating materials for higher efficiency. Professor, please.
Okay, thank you. Okay, so thank you for welcoming me. It's an absolute pleasure to be here at VinFuture Prize Symposium. So, thank you, Professor Green, for the introduction, for your pioneering work, actually, that demonstrated how silicon went from just few percent to 25, right? Over 25 now, so reaching this limit that one material can do. So, sorry. So, right now, as we are approaching limits of towards 29%, right? And we've proven that silicon is reliable and efficient. The problem right now, of course, that by 2050, we need to increase, or the demand on energy will increase by 40%. So we need to install in the next few years up to 3 terawatts on solar cells. Then you will reach limitations in space, in land availability, and materials. So we need to take a look on the sustainability of these installations. So, and this has been mentioned already, we can think of increasing the efficiency, so and decreasing the need for land space by introduction of tandem silicon solar cells with other materials. So you can think this of almost trying to catch the rainbow, right? If you have just silicon, you catch one color. But in order to make a very efficient solar cell, you need to catch the rainbow. So already catching more than one color. If you introduce another layer, you can go up to 45%, right? So, and there are certain materials you can use to have this second layer on top of silicon to increase your efficiency of your solar cells, right? There are several candidates that has been mentioned, for example, CIGR solar cells or 3 to 5 materials. The problem with those materials, of course, is the availability of rare materials there. So there are limits. And their limits are before we actually can make enough energy. So we need to focus on introducing materials that are readily available and abundant. And perovskites is a material that could bring us over the edge of 1 terawatt production. Right? This has been already mentioned, that you have certain criteria if you introduce new materials. Right? You need to consider how complex is the manufacturing, how sustainable can you produce them, how is the availability of these materials worldwide. Right? So on perovskites, right now seems to be the best solution we have. Right? It's been discovered already a long time ago by a Russian scientist, actually, 200 years ago, Lev Perovsky. And it's an incredible material. There's special crystals, right, that combining simple metals like lead and tin and others with simple organic molecules in a way that makes them extraordinarily good in capturing light and convert it to electricity. So imagine a material that we can simply print on paper, and it's still as efficient as silicon. So what makes perovskite truly remarkable is their versatility, of course. You can tune their properties by simply changing their composition, just like a toddler, mixing different colors together. You can mix and match the properties on top of another technology like silicon. So, and they absorb solar light so efficiently that we not only need less of materials, it also makes the solar cells more efficient. So right now, we already achieve over 34% efficiency in tandem silicon perovskite solar cells, right? What they do is you can use a much thinner silicon cell and a very thin perovskite on top, so at the same time you reduce the need of silicon by 85% by only using a few micrometers of perovskite on top. Right? So what you do is you enable a more sustainable manufacturing and you use less materials at the same time. It's a perfect composition for considering recycling the solar cell. Right? And as material scientists, and as we develop better, more advanced materials, we can do big changes on a very small scale. So we develop, for example, materials that's called self-assembly monolayers, so it's just a single molecule at the interfaces of the different layers of our solar cells that make a big difference. So it makes the solar cells more stable, more efficient, and more easy to recycle, for example. Right. This is where we come to the aspects of circular design principle that truly transform solar manufacturing. For example, the energy payback for silicon cells right now is just 1.5 years, right? So if you introduce these materials and advanced techniques on making them, you reduce the payback time to just 4 months. This makes this technology truly accessible worldwide. Most importantly, if you do that, you reduce the CO2 emissions by 50%. Not everything is perfect, of course, otherwise we would have already solved all our energy problems, right? So the problem is not within the photoactive materials, not the materials actually that makes the solar cell possible, but everything around us. For now, if you produce 1 terawatt of solar energy, you already consume 15% of silver, and silver is needed in the context of the solar cell. And the situation with indium that's required in so-called transparent metal oxides is even more critical. So to put this into perspectives, perovskite silicon tandem require about 2,000 tons of silver per terawatt of production capacity, right? So, but the target is very different. So what we need to go is we need to reduce the material use by 90% for indium and for silver. This will be absolutely critical. This is what energy materials researchers do, right? We develop carbon-based materials. We develop advanced encapsulation techniques. And these technologies are not just incremental developments, that they represent fundamental shifts in materials selections that could enable truly sustainable scaling, actually. Of course, there's always a question of lead and its toxicity and stability, because while it's very little, you have to consider that we only have 300 milligrams of lead per square meter of the solar cells. But newest research also shows that even a little bit, if just a little bit of it goes into your food production, you would increase, of course, the exposure to absolutely new levels. So we need to balance our need for energy and sustainability, of course, and consider how we deploy these new materials. What I see as a vision is that as we develop new materials, right, we could see that we develop materials that are truly adaptable and tunable, almost like seeing a solar cell as a living organism, where you develop materials that not just adapt to different environments, but also change over time. So imagine that you make solar cells that are not just last longer, but fundamentally rethinking how materials interact also with the environment. For example, they become more robust over the time you use, right? So this kind of transformative thinking, I think, is what we need as researchers to really look into a more sustainable future. So, and this is what we need, I think, as we go and inspire the next generation of scientists, is to build resilience and to learn from the nature to make a more tunable materials that adapt to new properties, from dynamic stability to self-healing properties. So, and of course, there's a limit on how much you can look into materials discovery. And I think that AI-driven materials discovery will truly help us to go to new combinations of materials, new developments, and really help us to discover new materials there, from really reduce our time and needs. So, and I think scalability will be the next hurdle, right? So as we look into innovative research with smart materials and circular production. Thank you.
Thank you so much, Professor Freitag, for your insightful speech and presentation. Thank you very much. Distinguished guests, ladies and gentlemen, and in the symposium today, we are honored to welcome an impactful scientist, Professor Seth Marder, Director of the Renewable and Sustainable Energy Institute at the University of Colorado Boulder, to deliver the lecture of Polymers for a Sustainable Future, Opportunities and Challenges. So Professor, the stage is yours.
I don't think, here we go. Thanks very much. Thanks to the organizers for inviting me. This is my first trip to Hanoi. It's been wonderful. Thank you, Quyên, for being a gracious host as well. So I'm going to talk to you about plastics, but the scientific term that we use is polymers. And polymers are everywhere. Although I'm very pleased to note that if you look right in front of you, what you would have probably seen in the United States and may still see in the United States would be a plastic bottle, but here you're seeing a glass bottle for your water. And that's something which I think is an indication of a change in mindset. So let me tell you what a polymer is. Polymers are strings of very small building blocks that are put together to make something that's a long chain of material. And they have interesting properties. And if there's just one of these things, it's called a homopolymer. And if there are different kinds of monomers, different materials that form the building blocks, you can make what are called polymers that are copolymers. So we think of polymers as plastics, but I think it's important to understand that polymers are ubiquitous in nature. Cell walls, trees are all made of polymers of natural building blocks. DNA is a polymer that codes proteins, which itself is a polymer. And these all have very unique structural and functional properties. So in 1907, Leo Baekeland discovered a material called Bakelite. And this was the first man-made large-scale polymer. And we talked about scalability. And scalability is both a blessing and a curse, as we'll see. So in the case of Bakelite, it became used, it's a cross-linked polymer, which means strands are glued together. And it became used in many, many different things. Like my old first telephone was made of it. A lot of different things were made of it. And then as time went by, people discovered that polymers are quote, miracle materials. They became used in many, many, many different things. And so we can do without plastic bags, but if we think about in the medical industry, polymers, plastic syringes, polymers that are used for tissue engineering are absolutely critical. For wires, okay, if you pick up a wire, it is undoubtedly covered with a polymer. It's used in electronics. And so it became explosive in terms of the growth of these materials. And in 1955, Life magazine talked about a throwaway living, where you use something once, you throw it away, you don't have to worry about it, life is easier. So amongst the challenges with polymers is that they're made from fossil fuels. Okay, those monomers are made typically from fossil fuels, things like ethylene, propylene. And as we know, these resources are not inevitably or indefinitely available, and there are consequences of using them. And so one of the questions is, okay, if we're going to be using these on the scale that we are, is this sustainable? And the answer is, it is not, okay? So this is a picture in the Maldives of an island of polymers, okay? Let me go back, okay? There are 6.3 billion tons of polymers. So one way of looking at that is the weight of 1 billion African elephants. Another way of looking at that is greater than the mass of every human being on the face of the earth. And that's in fact just in landfill, okay? The oceans are becoming filled with polymers. Your body, you've read about this, microplastics are being pervasive and they're affecting potentially our health. And so we need to think carefully about how we are going to address this issue. And I may be biased, but I think that polymers on the earth and in the ocean are a problem that is comparable to CO2 and methane in the atmosphere. So this is not a problem we can ignore. We have to address it. So how do we address going from what's called a linear process, okay, to a more circular process that Marina introduced? And there are three things that she also noted in her slide. One is to reduce the amount that we make and use. So for example, use glass when you don't need to use a polymer. One is to reuse things, okay? When I grew up in New York, our milk came in a milk bottle and you refilled it. We don't do that today. And then the other is to recycle, okay? And these are the principles of a circular process. And one of the challenges is that when we think about polyethylene terephthalate, which is used in water bottles, it's described as a recyclable material, which it is. However, only 9% of it actually gets recycled. So we need to think about how do we change the habits of people and the processes that we can use to recycle materials. And then we also need to think, how do we source the starting materials, the monomers? Do we get them from refining, or do we consider getting them from bioavailable feedstocks, okay? From, for example, things that we can grow. And so as we need to work on this, folks at one of my institutions, NREL, the National Renewable Energy Lab, have put together a consortium, and many people around the world have done so. I'm just giving an example about thinking about how do we have specific processes to break down polymers. When polymers were first made, one of the reasons that they were so popular is they were so stable. Unfortunately, they're too stable and they hang around forever in some cases, or nearly ever. How do we change the building blocks from getting our starting materials from fossil fuels to biorenewable materials, and then how to redesign these polymers so that they have exactly the properties that are needed, including the fact that they can be broken down and deconstructed, okay, and deconstructed to perhaps give the same starting materials that made them, and not simply mechanically deconstructed where they lose their properties. And this is the concept of circularity as it applies to polymers. So as you look at these things, we're thinking about using biomass as the building blocks. We're thinking about redesigning the polymers, and that can create a circular economy. And you can read more about one of the analyses of this in this paper. Here's an example done by some colleagues at NREL. Wind turbine blades are made of polymeric materials, plastics. They have to be very stable, but the issue of recycling them in the long term as they become more and more ubiquitous is a challenge. And what these folks did is they went to ground zero and said, let's not just use things the way we have in the past. Let's rethink using biomass, okay, as the starting materials. And what they did is they considered how to rethink the manufacturing, how to think the end-of-life actual properties and chemistry from the outset of design, not as an afterthought to go and make these things new. And how do we basically think about static properties so that they actually meet the performance requirements and the lifetime requirements. And this required an interdisciplinary setup, which involved literally beds for making these very large objects, for going through comprehensive mechanical testing, okay, analysis of recycling, and access to what are the bioavailable materials. And as Marina said, I think that AI and machine learning are going to become more important in this process of designing these materials. I want to also note that this required a highly interdisciplinary team of people working very closely. We can't think of the challenges that we have from a single discipline. Last couple of thoughts. We heard about solar cells. Okay, we think about silicon solar cells, tandem solar cells, but there's an awful lot of polymers in solar cells, and one of the challenges of recycling the polymers is that they are glued together, and it's hard to peel them apart. So one of the things that we're thinking about is how do we make the polymers that are used in solar cells more circular and sustainable? So my closing thoughts are polymers are and will be ubiquitous. We need high performance materials for the clean energy transition, but we want to make them as circular as possible. We need to make improvements in the design of polymers for circularity and to improve and preserve performance. But I think the last point that I want to make is that it's not just the technologies. We have to also change our behaviors as individuals if we're going to foster this clean energy transition. Thank you very much.
Thank you very much, Professor Seth Marder, for your wonderful presentation. And now is the time for the discussion panel today. I would like to welcome back to the stage Professor Richard Henry Friend, Professor Martin Green, and Professor Marina Freitag, along with our distinguished speakers. Welcome to the stage Professor Thục Quyên Nguyễn, Chair of the VinFuture Prize Pre-Screening Committee, Director of the Center for Polymers and Organic Solids at the University of California, Santa Barbara, to join the symposium's today's discussion. Please welcome to the stage panelists. Welcome. Would you kindly give a round of applause for our panelists today for the discussion of our symposium today? So scientists and panelists, the stage is yours.
Yes. We have one panelist who's not allowed to escape, yes. Well, our three keynote speakers really set out a very good perspective of both the opportunities and the challenges, and I think picked out some of the key features that we have to worry about. They generalize way beyond just the examples that we've heard about so far. So let me start. Let me turn to Quyên. Can I ask you to pick up on some of the issues about where we can go further with designs of materials, what the future there might be?
Yes, I think the discussion, the presentation highlights some important point, right? So right now, the way that we do research, that we keep focus on the efficiency and the performance, the lifetime, but it is extremely important to think about the sustainability upfront, recycling upfront, and in terms of the energy usage, I think incorporate AI into that. It's very, very important. It can really optimize the process. But at the same time, we have to think of all aspects of that. Because when you use AI, it means you also talk about data center. You also think about computing. And that also adding up into the energy usage when you use AI for energy research. And so I think that's we have to think about the full picture and not one aspect of that, just in terms of energy consumption pattern.
Marina, you mentioned AI briefly in one of your slides, and there's a lot of people ask: is AI the panacea? Is that going to speed things up? I wonder whether you can pick up one or two threads on what AI might mean for the materials world.
I think what AI will help us to do is to include sustainability and recyclability and materials development actually from beginning on. It will help us to look and to screen through materials which are already fulfilling these requirements from beginning on. I think what we need to be careful with right now is to balance the use of AI versus how much energy it costs us actually to use it. I think that will be very important as well.
What I think I understand about AI is that you need data sets.
Yes.
And we're quite good in some of the upstream stuff, the research we like to do, given free choice in universities. But a lot of the issues that really matter for the energy space are long-term stability, understanding what goes wrong. I just wonder how good are we at accumulating the data that allow us to learn from that, maybe with AI assistance?
So at least in the organic solar cell that we have seen, we published paper, and basically that pretty much it. So our group 4 years ago tried to use AI, machine learning, to learn from all the data available. But the big challenge that we don't have a really good platform, at least in the organic solar cell community, to store the data and to share the data that can be beneficial to use AI to accelerate the further development. So I think that the first step that we need some sort of data center where everybody can deposit the data in there, so to advance this particular area.
Marina,
I would like to add, so it's just mentioned, AI is only as smart as you make it, right? So you need data, you need to teach AI to be smart. For that you need an immense amount of data. And this, we don't have this yet. But what we can do is actually, another aspect is digital twins. So we can simulate, for example, solar cells and solar materials and entire installations and look at it in a digital world, how they progress over time before we actually implement them in the real world.
Yeah, I could just add some direct experience of one of my students who has set up a AI for solar cell material development in the University of Hong Kong. And I was just talking to him the other night, and he was saying he's finding AI very valuable in accelerating the search through different materials. So we use, ab initio computer simulation of some of the materials that I showed in my slide that we're looking at for possible tandem stacks onto silicon. But he was saying that with the AI, applying AI to that search, he's able to cut down considerably on the amount of time he has to spend doing fundamental simulations, in that the AI is able to search through the data he's already generated from those simulations and provide suggestions, I guess, about which direction the search should be continued. So we've spent a lot of time searching through materials one after the other, but the AI can provide a shortcut in your search through the possibilities. So he's a keen advocate of the role that AI is going to play in finding some new photovoltaic materials.
Seth?
The AI, I think, has certain challenges that are not of the technology, but of us. And one of the challenges I'll just talk about with perovskites is that many people report results on perovskites, but very few people actually report accurately how they've gotten those results, how they've made the materials, and how they've measured these properties. And so I think that this is places where large centers like Martin's or the Helmholtz Center in Berlin or NREL can help provide standardization and improve the quality of the information that we gather so that the AI can be more effective in helping us with solutions.
Let me move the discussion along a little bit. Marina, you put in some really interesting numbers. How much silver we need to produce a terawatt of solar cells a year. Back in the 1950s, there was another scare that we were going to run out of silver because it was all used for photography. Silver halide, which is the basis of old-fashioned photography, we used a lot of silver. So that was driving the price of the futures prices for silver up. And then Kodak worked out how to use less. But that's now being replayed as one of the elements you don't think about when you think of solar cells, but you just highlighted that it was there. And then we come to lead, which is present if the perovskites are commercialized, not much of it, but nevertheless widespread. But we have lead already in the batteries we use in regular cars, and some success in recycling it. How well are we doing? I mean, Seth, you were picking up on that as well.
Well, we were talking about this earlier. Unlike in plastics, where I talked about 9% of PET being recycled, in the United States, with car batteries, 97% of the car batteries are in fact recycled. And they've really optimized the conditions for separating out the parts, getting the lead, and actually reprocessing the lead into a useful form. In the perovskites, it's a slightly more challenging situation to do it. But I do think that the technology, so there are two issues. One is like if a solar cell breaks and the material escapes. The other is if you recycle it. I think that the reality of the toxicity issue is there, but the amount of lead and the likelihood for it to get into the environment is maybe a little bit overstated in certain places. I think the recycling of the lead, I think the chemistry is actually there to recapture the lead. And the question really comes down to not one of whether we can do it, but can we do it really economically? And I think that that's probably still being worked out.
This does seem to be a message that we hear more often, that we have the technology, we need to use quite a large fraction of the periodic table now to get the best solutions. That when we use materials like lead, and of course cadmium is also used in another variant of commercialized solar cells, we know these are toxic. We know we can recycle. Whether we do or not is a choice. Are we doing okay? You were giving quite a positive message, Seth. But Quyên.
So I think that's something that we need as the scientists to go out there and to interact with the consumer, but also policymaker. If you give people a choice, we're talking about plastic earlier, only about 10% of recycling, talking to company, and they said, well, it's much more expensive for us to use recycling plastic. We're much cheaper to make a new one. And so I asked them the question, but how about the responsibility with the society, with the environment, right? So I think that where all of this one, the same with PV, and right now we're talking about, we start putting all the module, the panel out there, and they pile up the earth. And they also say the same thing will be cheaper to make a new PV module. And I think that's why we need also policy maker to come in. And there are already issues how to put that recycling, the responsibility of the consumer or of the company, right? And so I think policy maker will be important in the future to resolve it.
So there are sort of different elements. I mean, one is that materials handled well are okay, but we need to recycle them carefully when they are toxic. There are these conversations or discussions as to which element do we run out of first? Is there enough material out there to support these huge technologies? And I think with solar, we might be okay. Martin, you're...
Yeah, certainly with the silicon technology, as was mentioned by Professor Freitag, the silver is the main issue in that we're now using 15% of the world's silver supply in solar. Fortunately, the uptake of solar matched well the decline in the use of silver for photography that you mentioned, so that the solar sort of filled the gap that was left by the declining use of silver in photography. But obviously, with the industry growing so rapidly, so the amount of solar panels being produced is doubling every 3 years, and it has done for decades. So, you know, if you're using 15% and you didn't reduce the amount of silver, you'd be up to, you know, 30% in 3 years, and then 60% not long after. So, you know, obviously something has to be done. But we've marketed two technologies, one to BP Solar in the 1990s, and they sold that technology for 30 years as their Saturn solar cells were the most efficient solar panels you could buy during the 1990s, and that used a silver-free technology, and the panels came back with very good report cards on their durability and everything. So it is completely possible to get rid of the silver from solar panels, as demonstrated by that, you know, that experience of BP with silver-free modules. You know, the problem is the solar panels are very reliable, and manufacturers now offer warranties from between 25 and 40 years. So when you're offering a product with that type of warranty, it's very dangerous to change any material ingredient within the panel, or you don't know what the outcomes might be 20 or 15 or 20 years down the track. So, you know, that's providing the real disincentive for changing away from silver now, is the unknown risk of making such a transition. But technically it's possible to change from silver to copper or even aluminium as the metallization in silicon cells. So with some of these other technologies, you don't have as many options because they're more reactive, and you're more restrained in the choice of your metallization that you can use. But certainly with silicon technology, I don't think there's any inherent material constraints in the use of it to supply all the world's energy, you know, by 2050, as some proposing would be a really good idea.
So I'm just trying to just picking up on your sort of exponential growth in production of solar. Your graph went out to a terawatt a year. Was that by
2027.
2027, gosh, that's quite soon.
Yes.
Just to give and very helpfully, you point out that it's, 700 watts per panel, so we'll be producing about 1.3 billion panels a year, which is quite a lot, isn't it? But exponential curves don't carry on forever. This is something that rather baffled some of our politicians during the COVID pandemic, the ones that read classics rather than science. But where does the exponential curve stop? When does solar when does it saturate the demand for energy? How much do we need to produce a year to get us to net zero?
Yeah, so one of my colleagues has looked at this reasonably carefully and just looked at how many panels we would need to supply, you know, all the world's energy. And, you know, it's something like 90 terawatts of installed solar that you need. And then if you work from 90 terawatts, and if the panels have got a 30-year life, you can work out the replacement rate there. So he believes that's the optimal annual production rate, which is about 3 terawatts a year it works out at. I hope I've done the sums right there. So we're likely to reach that level, you know, in the early 2030s, somewhere about 3 terawatt a year. So he can see this, if things go to his plan, you see this steadily or rapid increase up to this 3 terawatt, and then a bending over the curve and a steady 3 terawatts a year of annual production for eternity past then.
So I think we're going to have to finish this part of today's proceedings on that rather practical, achievable, but stretching target. This is all possible, isn't it?
Yeah, and I guess the history of solar photovoltaics has been that actuality has exceeded every expectation. So it's hard to find any predictions that we'd be at this level of photovoltaic utilization, you know, going back, you know, even 10 or 20 years. So it's been a history of exceeding expectations. So I think the reality of reaching 3 terawatts by the early 2030s, is quite high. So that could well be the scenario that we follow.
And we will learn to be, we need to learn to be responsible citizens to tidy up the mess as we generate it. But we can decarbonize. It's a good message. I think, so let's stop there with the conversation just within the panel. I think we move now to some questions from the audience and that have been generated earlier.
Yes, thank you very much for your wonderful discussion. Would you please kindly give a round of applause for our panelists today for the discussion panel with the first symposium. And now we're coming to the part that all the audience waiting for the whole hour that connect to our top scientists in the world. And now it's the time for the Q&A session. So I really want to see and to hear your voice with the questions by waving your hand. Yes, I can see many hands over there. So yes, the lady in black. So our staff can assist you with the mic. Thank you very much. The first question.
Hello. Thank you very much for interesting discussion. If we talk about the future possibility to recycle energy materials, is that easier to do that with organic energy materials?
Yes.
Compared to inorganic ones?
I think that was a question about organic materials. Did I hear that correctly?
So could you repeat once again about your
question? Is it easier to recycle organic energy material, like organic solar cells, compared to inorganic ones?
So the question is it easier to recycle organic carbon-based materials like plastics, or the inorganic bits, the glass, the silicon, maybe the silver? Yeah. Can I turn to?
I'll just
Yes.
make a quick comment. And there are probably others who probably are more competent to answer this. When you recycle a solar cell, you're recycling a system. And the active material, the thing that absorbs the light, probably in many cases, may be one of the easiest parts, no matter what it is, to recycle. Okay? Many of these things are glued together, and although the organics can be dissolved, but there's an awful lot by weight, by mass, that's not the active material. So I think that the ability to recycle organic solar cells, or solar cells that are tandem with organics versus other things, is probably not going to be a huge difference when you look at the entire system. That would be my instinctual answer to that. You've probably thought about this.
Yes, and I think there's another aspect, especially for organics actually. It's not to recycle them, but to convert them to a new material that can be used elsewhere. For example, there is a lot of research ongoing where people take these materials, for example, they convert them, maybe they burn them off and make carbon-based material, use them in batteries. So it doesn't have to become a solar cell again. It can become a material of very different property and be useful again.
Thank you very much, Professor Freitag and Professor Seth Marder. And now we are moving to the next questions. Yes, the man over there from second row. Our staff, please assist him with a microphone. Yes.
Hello, yes, sorry. As a simple engineer, I've had an interest in when we can start using some of the materials in structural buildings, in vehicles, and so on. So how close do you think you are to actually having a material which can be, say, put into a building, into glass, into metal, so that every building becomes a power generator, every vehicle becomes a power generator? So when do you think we'll get there in an economical way, so we can actually start using these materials at scale and at efficiency?
Thank you very much. And yes, moderator, who you wanna, the one who can answer these questions?
Let me turn to Quyên.
Yeah.
So in terms of for building integration, for material for building, so it really depends where. So I believe if you in a crowded building, I mean city like New York, where you have skyscraper, high-rise building, and the organic solar cell, because you can make into semi-transparent with different color, and that would be really great to put on any surface of glasses, or you can also laminate on the wall of the building. Now, they are also challenged with that, because if you put on building structure, you want to last for a long time, right? And so if you put between two pieces of glasses for a window, and then if you need to replace 30 years later, that could be a challenge. But then putting between two pieces of glasses can be much more stable. But now if you want to replace after 20 years or 30 years, so you have to somehow laminate from the outside. And so there are challenges there. There are the advantage of organic solar cell, but also there are challenges that we have to think about.
Thank you very much, Professor. Yes, Professor Seth Martin.
It is worth noting that there is already a company in Germany that has products on the market for organic building integrated solar cells for windows called Heliotech.
I think it's important to just remind everybody that the way the conversation has gone so far is about getting to net zero, and that is huge scale, very large areas required to generate electricity. It turns out there's adequate uncultivated land to be able to do that without too much negative impact, not uniformly distributed. But solar farms can get there. That's the big, urgent challenge. But in parallel with that, when you're putting up new buildings, it's crazy not to use the opportunity to get some solar in for free. It helps, but it isn't the main player in getting to net zero.
Thank you very much, professors and panelists. And yes, Professor Freitag, you want to raise your voice?
I think it also needs to be considered that 40% of our energy consumption is actually in buildings. Yeah. So if you can focus how you convert energy there, it will be very big impact, especially in high density areas.
Thank you. So, ladies and gentlemen, and now we have only one room for the last questions for our panelists today. So I want to see, yes, Professor.
I'm Nguyễn Thục Quyên from Freitag University in Hanoi. So my question is it even possible to recycle the rare element such as indium or silver in PV, in particular when the mass production accelerates? Because sometimes when we solve a problem, we maybe create another problem. Thank you very much.
I mean, in the past, that's been driven by economics. I mean, it turns out that it's quite a good industry to take sort of scrapped consumer electronics and computers to extract the gold that was used for plating contacts. That could be, if the price of gold is high enough, then it's worth doing that. What is the score for recycling of silver in the solar world, Martin?
Yes. I guess the issue with silver in solar panels was historically when the silver was reasonably cheap. There was a lot of it used in each solar panel, so panels of an earlier generation had a lot of silver in them. As I showed in one of my graphs, the market has grown exponentially, but the use of silver has not grown as rapidly because the cell designs have evolved so they don't need as much silver per panel. So it's becoming less and less attractive to recycle panels to extract the silver from them. So there's not enough silver in the panel to make the silver extraction a major economic force in deciding whether or not to recycle the panels. So the main constituent is glass, and just to give some perspective, I mentioned before that 3 terawatts a year was about the sustainable level for solar production to to provide all the world's energy, according to analysis by one of my colleagues. And if you look at the amount of glass that would be involved in that, it turns out that it would add about 40% to our present glass waste stream, from recycling glass from buildings and that kind of thing. So, you wouldn't really want to add 40% to the present glass waste stream, but it's not like introducing a problem of a completely different order of magnitude. I think it tends to be overstated, the issues that might be raised by converting from reliance on coal with the huge waste streams and fly ash and so on that are generated from that energy source, transitioning from there to solar, it's a relatively small scale problem that we're dealing with compared to problems that are already on the table.
Thank you very much for your words. And the Q&A session help us to close the first symposium today. We are so sorry that the time is limited, so that we cannot deliver all the questions, but don't worry. Our scientists are still around, and you feel free to connect and catch up with them. Thank you very much one more time for our panelists today, our top scientists from the world being here in Hanoi, Vietnam for our symposium. And one more time, thank you very much for all of our audience. And it is now for the time for the breakout session, and our panelists with the Connect room that we can join in the 3 different rooms for 3 assigned topics. And the session will last for 1 hour and close at 11:15. And don't forget to watch VinFuture Prize Award Ceremony premiered on VTV1, Vietnam National Television on the 6th December 2024. Goodbye and see you this afternoon. We love you all. Thank you.